So fuel cell engines convert from hydrogen directly into electricity. And this technology is not new. It has been developed by automotive companies like General Motors, Toyota for more than 2 decades. So now finally we can see some prototypes of fuel cell cars running on the street, like Toyota Mirai or Honda Clarity. But to take fuel cell cars to the next step, to go from hundreds of cars to millions of cars, there are several challenges that we have to overcome. There are technical issues, like for example, where does the hydrogen come from? How do we reduce the cost of hydrogen fuel cell engines? And then there are business issues, the competition with the hybrid and battery vehicles. Finally, there are social engineering part, like public acceptance and policy issues. Here at Thermal and Electrochemical Energy Lab, we're working on all of the technical issues to make the fuel cell cars possible in the future.
My key focus in the laboratory is the fundamental study of catalysts because that's where the fuel cell reactions happen. The work we do here at TIL is to synthesize and evaluate novel non-precious catalysts that can either efficiently convert water into hydrogen for fuel generation or combine hydrogen and oxygen to generate electricity. These electrochemical processes occur in each cell, which is just enough to light a bulb or a cell phone. But to power a car, we need hundreds of these cells stacked together. At this time, very expensive platinum is being used as catalyst for fuel cell engines, and our research will enable significant cost reductions for the large fuel cell stacks and hydrogen generator.
My background is in mechanical engineering, so my interest is in how gas and liquid flows and how heat transport works inside of the fuel cell. Ever since I was a kid, I've always been interested in car engines. Now I'm working on the next generation of engines for the future. So I designed how to effectively deliver hydrogen and oxygen to the catalyst so the reaction can occur more easily. One of the biggest challenges here at TIL is removing heat and water from the fuel cell engine because those are the byproducts of the chemical reaction. If the heat cannot be removed, the membrane will melt. If the water cannot be taken away, it is like a fire being quenched and the reaction will shut down.
Before becoming a university professor, I spent more than 6 years working for General Motors to develop fuel cell cars. This hands-on experience helped me to know how to scale up pure research to real applications. So in our lab, we don't just develop novel catalyst material and test them in a beaker. We also spend a lot of effort to integrate these nanoparticles with polymers to make a fuel cell. The fuel cell is almost identical to the ones used in the car, so we can test them directly in the lab. There's a lot of applied developmental work, like mixing the catalyst ink and testing the rheology of the ink to see how it deforms under shear force. Further, we develop computational models to simulate fuel cell performance, so we can compare those with the experimental data of the actual cell that we built in the lab.
Fuel cell technology can be used in many other applications. Refrigerators, air conditioners, and washing machines can be powered by hydrogen in the future.
Right here in the TIL lab, we're even working on integrating fuel cells with drones, so that way flight times can be as long as 2 hours per trip.
Overall, our goal is to use natural resources like sun and wind to create a clean and sustainable hydrogen community that can power our home, our cars, and many other energy needs.